So in this video, we're going to introduce substitution and elimination reactions, and we're going to focus specifically on SN2 reactions. So there are two main reaction categories that we'll notice throughout the course. More specific reactions falling sort of into these categories. We just saw alkenes and alkynes undergoing a host of specific reactions falling into mainly the electrophilic addition category. And we spoke of carbocations and their relative stability. And in one of the reactions, we saw alkynes being used to make new carbon-carbon bonds. And we followed up with, in the second step of that reaction, with the substitution reaction. So, for example, we just saw that terminal alkynes can be weakly acidic. And they can be deprotonated to form carbanions and then used to form new carbon-carbon bonds. So this hydrogen in the last bit, so when we were doing alkenes and alkynes, we were like, all right, if you were to hit this with a pretty strong base, so sodium amide, which is a source of NH2 minus, it's a pretty strong base, you would take that hydrogen off of the alkyne, and then it would form a carbanion that could then attack something like this. That second step would produce a new carbon-carbon bond. And that second step is actually a substitution reaction. So what is going on here? So substitution reactions are not the same as addition reactions. It looks like you're just adding a methyl group, so it seems like it's an addition reaction, but they're slightly different. So in a substitution reaction, the electronegative group on one molecule is swapped out for the incoming nucleophile. So in the example that we just looked at, if you were to deprotonate that alkyne, you'd have a carbanion, so you'd have that lone pair of electrons on the carbon with a negative charge. That thing is going to come in and attack the methyl iodide. That's going to be, and the iodide would be your electronegative group, right? That's going to leave, and you're going to be adding the methyl group. So in an addition reaction, though, a group is going to be added to a species, but it doesn't take the place of another group that was already there, right? So when we were talking about the addition reactions of alkenes, we were like, all right, the alkene is going to come in and act as the nucleophile. It's going to grab an acidic hydrogen off of another molecule, and then whatever's left on that molecule is going to come back in and attack as a nucleophile, right? It's going to attack the positively charged carbon that's left over after one of the carbons in the double bond has been left electron deficient. So they're different, right? In a substitution reaction, we're swapping out an electronegative element for some other group. In an addition reaction, we're adding a whole other group to a positively charged or an electron deficient carbon after we have taken the pi bond or the electrons in the pi bond and snagged a hydrogen off of another molecule. So they're different reactions. So organic compounds that have an electrophilic group bonded to an sp3 hybridized carbon can undergo these substitution elimination reactions. We're not going to start out with alkenes and alkynes. We're going to start out with alkyl halides, for example, or alcohols, or some kind of sp3 hybridized carbon. So a carbon with 4 different groups, or at least 4 electron domains, right, on them. And these organic compounds that have these electrophilic groups bonded to an sp3 hybridized carbon can undergo a substitution or an elimination reaction. As it turns out, with the elimination reactions, we end up making alkenes. So for example, we could have something like methyl bromide, and to that we can add something like hydroxide. On the other side of this, we're going to get methanol plus bromide. So you can see, and we're not always going to draw all these like dots in on everything unless they're necessary, but the hydroxide is going to be used as our nucleophile. That's our little symbol for a nucleophile. And this right here is going to be what we call a leaving group. On the sp3 hybridized carbon. So that's our electrophilic group on the sp3 hybridized carbon. And the methyl group, that carbon in that molecule, methyl bromide, is our sp3 hybridized carbon. So hydroxide is going to be viewed as a base and also as a nucleophile. We'll talk about what the difference is between those two in a bit. But this is a substitution reaction. In elimination reactions, what we have is an electronegative element. So some electronegative atom or an electron withdrawing group on one molecule is going to be eliminated along with the hydrogen from an adjacent carbon. So for example, we could have something like this plus OH minus, which can act as a nucleophile or a base. And what we're going to get is we've removed a hydrogen from an adjacent carbon, so that methyl group there, and we've eliminated the leaving group. We're going to get water plus bromide, right? So the hydroxide is going to come in, it's going to deprotonate the carbon that's next to the carbon that bears the leaving group, or in other words, the electronegative group. Those electrons are then going to collapse between the two carbons and the leaving group will dissociate. So we end up with an alkene. Substitution eliminations are kind of a big deal because they allow us to easily convert these molecules into other compounds, and they are widely available. So these alkyl halides, we're going to be focusing on substitution elimination reactions of alkyl halides, and they're widely available commercially, and they're relatively cheap. So substitution eliminations are going to be pretty important to us. There are a couple of different mechanisms or mechanistic pathways by which substitution reactions occur. So we're going to focus on that in this video, at least one of those. So there are a couple of mechanistic pathways by which substitution reactions can occur. So each is going to involve the reaction of a nucleophile and electrophile. So we'll put that down. So each one involves the reaction of a nucleophile, abbreviated just NU. That's the thing with the electrons, and an electrophile, E+. So we'll just say it doesn't have to have a formal positive one charge, but it's deficient in electrons. So that's sort of like our sort of symbology for an electrophile. So this is going to be our nucleophile. And this will be our electrophile. So the nucleophile is going to be nucleus loving, right? And the electrophile is going to be electron loving. So this is where these two are going to intertwine. In both cases, the electrophile is going to be substituted for the nucleophile. So we call these reactions nucleophilic substitution reactions, because in each case, we'll have a molecule that has an electronegative element that's going to be substituted for the nucleophile. So we call these nucleophilic substitution reactions, and we designate the mechanism with either a 1 or a 2 to indicate its molecularity, and that is data driven. So we will indicate the type of substitution reaction by its molecularity. And this is all going to be based on data. And that data will be kinetics. So if you remember from Gen Chem, we decided how many molecules were sort of involved in the rate determining step. So the concentration of what reactants are involved in the rate determining step, or the slowest step. If you've got one molecule that is involved in the slowest step in the entire process, we call it unimolecular. And if we have two molecules involved in the slowest step, or the rate determining step, or in other words, the step where the activation energy is the highest, so you have the highest bump in the reaction progress diagram. If the two molecules are involved, we refer to that as a bimolecular process. So the mechanisms are going to be determined experimentally. They are not something that chemists sort of just make up to explain how our reaction occurs. They cannot be proven. They can only be disproven. And so on the stuff that we learned in Gen Chem, we kind of learn a lot about a reaction mechanism through the kinetics data. We can tell how many molecules are involved in the slowest step of the reaction. So in other words, the concentration of each of those reactants matters in the slowest step. If you double the concentration of one of those compounds, then you'll double the rate of the reaction. In a unimolecular mechanism, if you have two reactants and you double the concentration of one of them, you'll double the rate of the reaction. If you double the concentration of the other, but holding the other one constant, then nothing happens to the rate. So kinetics data can tell us like, hey, this is like, you know, one molecule is involved in forming the transition state or achieving the transition state, or one molecule or two molecules are involved in the rate determining step, or in other words, the slowest step. So we're going to start out with our bimolecular process for a nucleophilic substitution reaction, and this is going to be otherwise known as the SN2 reaction. So the S stands for substitution, the N stands for nucleophilic. So we have a nucleophilic substitution reaction. And it's bimolecular. That's what the 2 stands for. So if you remember from general chemistry, that means that there are 2 molecules involved in the slowest step. So let me give you just sort of like a simple sort of example reaction. We could have something like methyl bromide, and we can allow this to react with the hydroxide anion. What this gives us is methanol and bromide. And the rate law for this is going to be some rate constant, K, and it's going to be multiplied by the concentration of your alkyl halide times the concentration of your nucleophile, or in this case, your base, which is your nucleophile. So this rate here is going to be your rate constant. It's just a number. It's experimentally determined. The size of this thing, so the magnitude of the rate constant, speaks to the difficulty the reactants have in overcoming the activation energy, that little energy barrier. And so that is, how hard is it for these reactants to achieve the transition state, which is that state between reactants and products. The larger the rate constant is, like the bigger that number is, the lower the energy barrier is, or the lower that activation energy is. And so therefore, the easier it is for the reactants to reach the transition state. In other words, the larger that K value is, the faster the reaction rate will be. So the faster the reaction will be. This right here is going to be your electrophile. This will be your nucleophile. The rate law, so this expression here, rate equals K times the concentration of both of your reactants. So that rate law tells us which molecules are involved in the transition state of the slowest step. And if we have data that suggests which molecules are involved in the transition state, we can then design a method. That means we can tweak the reaction conditions, like the temperature, the solvent, all that stuff, the concentration of one of these things, right, to support that transition state. If we support the transition state because we believe that both of these molecules are involved in achieving the transition state, we are effectively encouraging the forward process in the reaction. So we've got data, in other words, experimental observations that suggest the SN2 mechanism. So some of these data include the rate determining step, or the rate of the reaction. So by the rate law, the reaction rate, how fast it is, depends on the concentration of the alkyl halide and the nucleophile. So the electrophile and the nucleophile, right? The concentration of both of those is going to govern the rate of the reaction. And the other thing that we find experimentally is that as the alkyl group, or the size of it, as the alkyl group on the electrophile so in other words, E plus, as that gets bigger, or bulkier, right? The reaction rate slows down. So the smaller the alkyl group on the electrophile becomes, the faster the reaction occurs. So in other words, you could say, and this is just based on experimental evidence, if we had methyl bromide, it would react faster than ethyl bromide, which would then react faster than 2-bromopropane, which then would react way faster than T-butyl bromide, which, by the way, under this particular mechanism that I'm about to show you, this reaction doesn't occur. That alkyl halide is too sterically hindered. So this is a methyl halide, and this is going to react the fastest. There's really kind of nothing in the way. This is a primary alkyl halide, this is a secondary alkyl halide, and this is a tertiary alkyl halide. These react the slowest or not at all. So the other thing that we notice is that when the reaction occurs on the alkyl halide carbon that is asymmetrical, so if I had a chiral carbon on my alkyl halide, you only get one stereoisomer that forms, and the configuration is inverted relative to the starting alkyl halide. So when the reaction occurs on, on an alkyl halide, carbon that is chiral, so if there's stereochemistry associated with that carbon, only one stereoisomer forms, and the configuration is inverted relative to the starting material. So how do we visualize this? So we could take something like, take something like this. We could just draw our tetrahedron. So here we have a carbon, right? And it's got 4 different groups on it. So this is S2 bromo butane. And we're going to allow this to react with a nucleophile, something with a lone pair of electrons, right? What we get when we attack this thing, the molecule that we get as a product is a substitution product where we have swapped out the bromine for a hydroxyl group. But not only that, we notice that we get the R isomer, not the S. So this is R2 butanol. So we've inverted the stereochemistry, plus bromide, whatever, right? We care really only about the organic product here. So this leads us, so this is, at the end of the day, you get what you get, right? In the lab, you analyze it and you're like, what the heck just happened there? I've got an inversion of stereochemistry. I have a substitution product with an inversion of stereochemistry. So we propose, based on the data, a mechanistic pathway by which this reaction could occur. So in order to get the substitution with an inversion of stereochemistry, sorry about that, we draw this out like this, and we say that the hydroxyl group is going to come in and it's going to attack the backside of the carbon that bears the leaving group, and the leaving group is going to leave. And this is going to happen all in one step. So this is a combination of all of the data, not just the stereochemistry, but also the fact that the concentration of the nucleophile, the hydroxyl group, right, this OH minus here, and the concentration of the alkyl halide are participating in the rate determining step. They're participating in the slowest step of the reaction. And as this happens, because we only have 2 reactants, right, and both, the concentration of both are taking part in the rate determining step, or the slowest step, we say this happens in a concerted fashion. It's a one-step process. These are the only 2 ingredients we have in the pot, and both of their concentrations matter in the rate determining step. So we say this is a one-step process. It involves everybody in the flask, right? And then in order to get that inversion of stereochemistry, we say that the incoming nucleophile needs to attack the carbon from the backside, and the bromide, or the leaving group, needs to leave. So the nucleophile attacks the backside of the carbon that bears the leaving group. Your nucleophile is your hydroxyl group. Your electrophilic carbon is going to be that methyl group, that carbon there, the sp3 hybridized carbon that bears the leaving group, which is the bromide. That's going to attack, the nucleophile is going to attack the backside of that carbon, and it's going to displace it. And that's going to leave us with a compound that, if this actually had some stereochemistry associated with it, we'd see an inversion. So what does this look like sort of graphically? You can always draw an energy plot relative to reaction progress. What we have here is our starting materials. We have some activation energy, and then we have product. And this right here is going to be our transition state. So in this case, what we have is methyl bromide plus hydroxide. We can actually draw that transition state by saying, here comes our hydroxide. It's going to be attacking the carbon that bears the leaving group. As the carbon's being attacked, the leaving group leaves. This is our transition state. This thing doesn't exist. No one can isolate this. We just imagine that this was kind of what it looks like, right? It's the in-between state. And now at the other end, you get the product. So if the carbon that bears the leaving group has a huge substituent on it, like if it's got some bulky stuff other than hydrogens, it's a little harder for the nucleophile to get in there, right? It's harder for the nucleophile to attack a carbon that's got bulky substituents on it. And so if that happens, if that carbon has bulky substituents, like something other than hydrogen, for example, the rate slows down. We call that steric hindrance. So if the electrophilic carbon has bulky groups on it, the reaction rate slows down. We call this steric hindrance. So when we were talking before about the rate of reactivity with the alkyl halides, a methyl halide is going to be the most reactive because that's what you're looking at right here. The only groups that are on the carbon that bear the leaving group are going to be hydrogens, right? With a primary alkyl halide, you've got some R group, a couple of hydrogens, and then your leaving group. With a secondary alkyl halide, you have two R groups, a hydrogen, and then your leaving group. And with a tertiary alkyl halide, we're like, all right, that doesn't undergo an SN2 reaction. Because in that case, if you had a tertiary alkyl halide, you've got that carbon bonded to three other R groups plus your leaving group. And then the nucleophile can't even get in there and attack the carbon, right? So experimentally, we just find that these reactions, the SN2 process anyways, does not occur. It doesn't mean a substitution reaction does not occur on a tertiary alkyl halide. It just means that it may undergo a different mechanistic pathway, that's all. So let's look at some factors that will affect the SN2 process. So remember, this is a nucleophilic substitution reaction, and it is bimolecular. It means that both of the reactants concentrations are going to matter in the slowest step of the reaction. It is a one-step process. So this is a concerted process. You can tell just by looking at the reaction progress diagram, we only have one activation energy. This right here is our activation energy. There's one. If there were two steps, we'd have two of those. Kinetics tells us that both concentration, or at least the concentration of both reactants, are going to come into play with the reaction rate. And if there are only two reactants, then it must be a one-step process, right? So the factors that are going to affect the SN2 process, well, think about everybody that's going on in the flask. The first thing I can think of is going to be the leaving group. We usually just abbreviate that LG. The more stable that thing is after it leaves, the better it is at dissociating. So in other words, we're looking at what leaves on an alkyl halide. The halide, right? So iodide is going to be a better leaving group than bromide. And that's going to be a better leaving group than chloride, which will be a better leaving group than fluoride. We're essentially looking for the weakest base. So the more stable, the better it is at leaving. We're looking for the weakest base. The weakest base is going to come, so it'll be the conjugate base, right, from the strongest acid. So in other words, we could look at the pKa of the hydrogen halide. The smaller the pKa of the hydrogen halide is, the weaker its conjugate base is going to be, because the smaller the pKa of HX is, the stronger the acid. And the stronger the acid, the weaker its conjugate base. So I've got a -10 for the pKa of hydroiodic acid, HI, I'm sorry. And that means iodide, with the lowest pKa, meaning it was the strongest acid, right? Hydroiodic acid, compared to hydrobromic acid with a pKa of -9. So that means that hydrobromic acid is going to be just a little bit weaker, although still a strong acid, but a little bit weaker than hydroiodic acid. That was going to be a little bit stronger than hydrochloric acid. So in other words, then chloride is going to be a little bit stronger of a base than bromide. And then hydrofluoric acid is the weakest acid of all. pKa of that is like 3.2, which means that fluoride is going to be a relatively strong base. So the weaker the acid, the stronger its conjugate base. The stronger the acid, the weaker its conjugate base. When we did the review of Gen Chem, and I said to you, pay attention to pKa's because we're going to be using those to compare the reactivities of either their conjugate partner or them, right? This is what I was talking about. So you can decide how great the leaving group is going to be based on the pKa of, after you protonate it, what would you get, kind of thing, right? So in other words, the relative rates of reactivity for even just a methyl halide, we use X as our sort of slang symbol for a halogen, will be methyl iodide is going to be more reactive than methyl bromide, which will be more reactive than methyl chloride, which is more reactive than methyl fluoride. Because when you attack that carbon and that leaving group leaves, iodide is going to be more stable than bromide, which is going to be more stable than chloride, which is more stable than fluoride. The other thing that we have to worry about is going to be the nucleophile. So the thing that's doing the attacking. So in other words, this is going to be the species with the lone pair. So with the electrons used to attack the electrophile or the electrophilic carbon. So these can be neutral molecules that just happen to have a lone pair of electrons, like water or ammonia or something. This can be a neutral molecule or a negatively charged species. Sometimes we think of those as a base. So what then is the difference between a base and a nucleophile? Because when we move into elimination reactions, we're going to be using bases, right, to deprotonate carbons. When do bases become nucleophiles? What's the difference, right? So we should probably talk about that. Basicity is a measure of how well a compound, in other words, a base, which you identify from Gen Chem what the base is, will share its electrons with a proton and, in other words, stronger bases share better than weaker bases. So you're basically asking yourself, like, how awesome is this base at deprotonating some other molecule? So that's basicity, right? Nucleophilicity is a little different. Even though a base can be a nucleophile, the way we measure it is a little different. Because you can use a base as a nucleophile. You can use a neutral molecule as a base. We've seen water behaving as a base, right? So no big deal. Has lone pairs of electrons, why not, right? So this nucleophilicity for us, this is going to be a measure of how readily a compound, and we're going to refer to that as the nucleophile. So Nu. So a measure of how readily a compound is able to attack an electron deficient atom on some other molecule. And I'll say species because sometimes we can have a nucleophile and an electrophile on the same molecule. So as we move through the course, we'll see some intramolecular substitution reactions or elimination reactions or whatever. And it's all because you've got all the goods just on one particular species. So a nucleophile or nucleophilicity is a measure of how readily a compound is able to use its lone pair of electrons or extra electrons, like you could have pi electrons, to attack an electron deficient atom on some other species. The better the nucleophile, the faster the SN2 process. So we'll put that down. The stronger the nucleophile, sometimes we look at that as more basic. The faster the SN2 process. This is all provided that you can do an SN2 process, right? So if you have a tertiary alkyl halide, it doesn't matter if you're dealing with a super awesome base, it's not going to undergo an SN2 process. There's another process that it will undergo, but it won't be an SN2. You want a nucleophilic substitution reaction that is bimolecular. You want a teeny tiny little super strong nucleophile. That's what you're hoping for. If the attacking atoms are about the same size, so if you're wondering, like, how do you know about the bases, right? So if the attacking atoms are about the same size, stronger bases are better nucleophiles. So in other words, if I'm dealing with something that would be relatively close in size to some other species, the stronger the base, the better the nucleophile is going to be. Like, for example, I could say that the amide anion, which is a stronger base than hydroxide, is going to be a better nucleophile, which is about the same size as the fluoride anion, which of these three would be the weakest nucleophile. They're all decent nucleophiles, but the amide anion is going to be better. They're all relatively close in size. A species with a negative charge is going to be a stronger base than its neutral counterpart. So a species with a negative charge is a stronger base. Then its neutral partner. What do I mean by that? I mean that you could compare hydroxide to water. So here we have OH minus. That's going to be a better nucleophile than its neutral partner, water. Methoxide, CH3O minus. So we've deprotonated methanol, will be a stronger nucleophile than methanol. See, these are just conjugate acid-base partners. The neutral molecule is going to be a weaker nucleophile. Amide anion is going to be stronger than ammonia. Notice how they're just only different by 1 proton. And then we also notice that nucleophilicity, oops, is affected by sterics. In other words, the size of the nucleophile also matters. So a bulky nucleophile, we already looked at the alkyl halide, which is the electrophile, and we said that, a bulky electrophile is going to slow down the SN2 process. A bulky nucleophile will also slow down the SN2 process because it can't approach the electrophile as easily. So it cannot reach the backside of the carbon bearing the leaving group. As easily. So in other words, like a tertiary nucleophile, right? Some like instead of methanol, for example, we have like T-butanol or something, right? Some big fat nucleophile is trying to get in and attack some electrophilic carbon. So the bigger and bulkier the nucleophile, the harder time it has to get in there and do its attacking. So even though you have something like, even if I were to compare bases, so if I took a strong base, or I should say a stronger base, so if I've got T-butoxide, and I compare it to, say, methoxide, we know from Gen Chem that the more substituents we have on that carbon that bears the group with the lone pairs of electrons, we are bolstering that negative charge on that atom that bears the lone pairs of electrons, which makes it more basic. So T-butoxide is a stronger base but methoxide, because it's smaller, I mean, it is basic, it has a negative charge, right, is a better nucleophile. It's smaller. Easier to attack the carbon that bears the leaving group. So it's a better nucleophile because it's less sterically hindered. Okay, so that's the SN2 process. We have a concerted process where we've got a nucleophile attacking an electrophilic carbon that is relatively unhindered, right? And it bears a leaving group that can take off, can dissociate after that carbon is attacked. The product of the reaction has an inversion of stereochemistry. So if your starting alkyl halide was chiral, you would end up with the opposite configuration after the SN2 process is done. So this is a bimolecular nucleophilic substitution process. There is a process that occurs that is a unimolecular nucleophilic substitution process where the concentration of only one of the reactants is actually taking part in the rate determining step. And that plus the elimination reactions will be the focus of our next video.